Okay, so we'll start with an example problem, which is to do with application of centrifugal force again. So this time we have an open conical surface like this. So this surface is rotating about its vertical axis at an angular speed omega. And this is a rough surface with a coefficient of friction mu. This radius is capital R here, and this vertical height is h. Now there is a particle which is lying on the surface at a point which is at a height of h by 2 from the vertex. So an open cone is in rotation about its vertical symmetry axis. With uniform angular speed omega and a particle P. It's observed to be at rest on its inner surface as shown. Now given this radius is 12 meters, the vertical height is 16 meters, g is 10 meters per second square, and the coefficient of friction is 0.5. So the first part, find omega if there is zero frictional force acting on the particle. So we have to find the angular speed of the cone's rotation, assuming that there is no friction acting on the particle while it is observed to be at rest on the inner surface. Okay. And second part, we have to find the range of omega, that is from some minimum to some possible maximum value, for which the particle does not slip on the surface. So this is very similar to the problem we had done last time to do with the hemispherical surface, you'll remember. Okay, very similar kind of free body diagram. So the approach will be just about the same thing, okay, that the particle is at rest with respect to the surface. So it is best to make the free body diagram of the particle in the frame of the surface, which is a rotating frame. So you have to take into account the centrifugal force, and it is just equilibrium of forces. So just try out the first part. We'll discuss the free body diagram.
It's at rest with respect to the cone, right? So
Yes, with respect to that.
okay.
And in the first part, in addition to being at rest with respect to the inner surface or with respect to the cone, there is also zero friction acting. So that means there is no tendency for slipping for the particle. So friction is not acting. Right. So you start by making the free body diagram of that particle P in the cone's rotating frame. And in that free body diagram, now you show equilibrium of forces without the need for friction to act. Okay, so how many forces are there in the free body diagram for the first part?
So the weight of the particle, normal reaction, and centrifugal.
Yes, very good. So you have to now solve the equilibrium of three forces problem, right? So what is the direction of the centrifugal force?
Radially outwards from the axis.
So will it be horizontal, vertical? What type of force it will be?
Horizontal.
Yes, horizontal. Okay. And what about its magnitude? Omega is unknown, but it will be in terms of m omega square r, right?
Yes, sir.
So we are in this rotating frame, and the particle is, let's say, over here. So the centrifugal force acting on it is like this, radially outwards. So what is small r over here in the centrifugal force formula?
R/2.
Yes, very good. So small r over here is the perpendicular distance from this axis, which is this. Okay. Now that is where our geometry concept will come in, that this particle, it is lying at a position where this vertical height is half the total vertical height of the cone. So r by capital R you can see is h by 2 divided by h. So that will make it 6 meters. And what about the direction of the normal reaction force?
Perpendicular to the surface.
So that will be at 90 degrees to the surface. So now we'll have to work out the angle involved. Right? So if this angle here is theta, then this angle will be theta. So this angle is theta. So you can see theta is tan inverse of h by r. So it's 53 degrees. So now you can easily work out the equilibrium of forces. So this is the value of omega we get in the first part. Right, now in the second part, we have to find the range of omega minimum to maximum so that there is no slipping. and we have to incorporate the fact that the inner surface is rough. So for example, from this value of omega that we've calculated here, if you look at this parametrically, this omega is root g by r tan theta. Okay, so from there, if we increase the value of omega, what will happen? There's a tendency to slip up the inclined plane because the centrifugal force is increasing compared to the above diagram. So that can be prevented by friction acting down the inclined plane. So the more we increase omega, the more the tendency to slip up. So more and more static friction will start acting down the inclined plane till the static friction reaches a limiting value of mu n, in which case it is just about starting to slip. So limiting static friction mu n acting down the inclined plane will correspond to maximum omega. Okay. So incorporating that in your free body diagram, you can find out the upper limit of omega.
Sir, can the minimum value of omega be lower than this? Like if friction starts acting up the inclined plane, if we lower omega.
Exactly. So minimum omega, now you have to start looking at the situation where if you reduce omega compared to the upper value,
Yes, sir.
2 by 3 root 5, then mg sine theta dominates. Okay. Over centrifugal forces component up the inclined plane. So there's a tendency to slip down. So now friction starts acting up the inclined plane.
Yes, sir.
Okay, so now let us see what happens as we start increasing omega. So for omega equal to square root g by r tan theta, which was about 1.5 radians per second, there is no tendency for slipping. So friction acting was 0. So therefore, for omega greater than this value, okay, there is a tendency to slip up the surface. So static friction will act down the surface if there is no slipping. So this will correspond to a free body diagram where so we can see that so m omega square r's cos component is becoming greater than mg sine component. So static friction acts down the incline to prevent it from slipping. So this kind of situation comes in. So if we incorporate the components tangential and normal to the surface, so we'll see there is centrifugal components like this. Then there is mg's components. Which will tend to act like this. Normal reaction which will act like this. And finally, the static frictional force which will act like this. So the tendency for slipping is prevented by static friction along with mg sine theta, balancing m omega square r cos theta. And normal reaction is created because of the two forces, the two components mg cos theta plus centrifugal forces sine component pushing the object against the inclined plane. So now when we want to calculate the limiting condition here, so for limiting condition, the static friction maximum value is mu n. So from equation 1, we can substitute the value of static friction required to keep it from slipping. And from equation 2, we can substitute the value of normal reaction available. And from that, we can get the limiting value of omega. Okay, so the solving part of this is also a little bit tricky. So I'm first leaving it up to here for you to go through the free body diagram, the resolution of the forces and all that. Okay. And then you incorporate this and try to work out the value of omega. So when we take the equality symbol over here in this equation, that will correspond to the situation where omega is maximum before slipping starts, the maximum possible omega before the object has a tendency to slip. Okay, so let's understand the final equation. So from the above equation 1, you can see that the required static friction is m omega square r, sorry, cos theta minus mg sin theta. So this is the static friction which is acting assuming no slipping, and this cannot exceed the value of friction available, which is the limiting friction, which is mu into n, where n is mg cos theta plus m omega square r sin theta. Okay. So now we can cancel m on both sides and take omega square on one side. So if you take omega square on one side, you see you have cos theta minus mu sin theta, and that is less than equal to, take g on the other side. So you get sin theta plus mu cos theta. So this shows us that omega square r is less than equal to, or in fact I can take the r also on this side. So omega square should be less than equal to g by r into this whole term, sin theta plus mu cos theta upon cos theta minus mu sin theta. So omega in general should be less than equal to g by r. Now for this expression, I can divide the numerator and denominator by cos theta to express it in terms of tan theta. That will just make it more convenient to solve. Okay. So from this I can see that omega is less than equal to this. That means for no slipping, of course, for the no slipping condition. So omega's maximum value will be when we take the equality symbol. Okay. So that will be here. Now theta, remember, was 53 degrees and mu was 0.5. So tan theta is 4 by 3. Right, this is half. So from this we can get omega maximum in radians per second. Okay. And like this, now you can incorporate the second part of the question for omega minimum, where you will see that you have to just reverse the direction of friction, because now your mg sin theta component will dominate over centrifugal forces cos component, because you're reducing the value of omega. So friction has to act the other way. Okay, so this will give us a value of
Root
4 by
55 by
3
6.
plus 1 by 2 will give us how much? 8 plus
11 by
3,
6.
7 by 6, right? And in the denominator, we will have 1 by 3, so 3. So it's close to about 3. You can see compared to the above value when no friction was acting, it's almost double. Okay, now, similarly, on the other hand, if we reduce the value of omega, there's a tendency to slip down the inclined plane. So friction acts. Now, when we are doing the calculation, we can just simply incorporate the fact that there are the same forces, same equations, just the direction of friction is reversed. Rest everything is remaining the same. So assuming it's not slipping, so we can see here that so when we incorporate this, that we'll see that we'll get omega is greater than equal to. Now what we can do is instead of solving the whole thing, in the above equation, everything is the same except friction's direction is reverse. So just replace mu with minus mu. Multiply mu with a minus sign. That will make sure that friction's direction in the FBD is reverse. So we'll get this. Okay, so from this you will get Oh wait, I have a mistake here. This will be 5/3.
So root 10/3.
Root 5/6, no?
Sorry. My root 5/6.
Okay, so the range of omega, as you can see, is about from 0.91 to for the no slipping condition. Okay, so this is all about examples of circular motion with application of centrifugal force, etc. There is also an interesting problem to do with banking angle situation. So circular tracks with banking. So suppose a circular track of given radius is banked for an optimal speed of 36 kilometers per hour. So what this means that at V equal to V naught, a vehicle will not have any tendency to slip. So if mu is, let's say, 0.2 for a particular car's tires, find the maximum speed at which it can negotiate the turn without slipping that. Okay. So you'll see very similar kind of free body diagram we've discussed. So when we see the top view, and when we see the side view, the road is banked like this. So if we are in the rotating frame, we'll see that there is centrifugal force. We will write it as mv square by r. Weight and normal contact force. Now we know that for V equal to V naught, this happens. So there is no friction acting on the tires. So which in this case will become tan theta is 1/5. But for V greater than V naught, what will happen? There's a tendency to slip up or outwards. So friction will act inwards. So here friction will act like this, static friction. So from this we
Sir?
can, yeah.
So here too the centrifugal is acting along the horizontal.
Sorry, centrifugal is,
Acting along the horizontal.
yeah, because why it's acting along the horizontal? Because see the axis about which the rotating frame, in the rotating frame you're seeing the car rotating about which axis? Is a vertical axis now passing through this point. Understood, no?
Yes, sir.
So you incorporate the same equations. Okay. So resolve centrifugal force into components. resolve mg into components. We have a normal reaction like this. And now because V is greater than V naught, so friction has to act like this. And then from this you can find the limiting condition that the friction should not exceed mu n. So it's exactly same as, I mean, in terms of solving, it's very similar to the last question we have done, only we'll find the limiting value of V instead of the limiting value of omega.
Sir,
Okay, so let's see the value if you have calculated. So this is another important type of problem for the application of banking angle concept. Okay, that not only the relationship between the optimal speed and the angle of banking for the zero friction condition, but given the coefficient of friction, what is the maximum speed at which? Okay, so when we incorporate this over here, we can see that the friction that is acting is equal to mv square by r cos theta minus mg sin theta, and this should not exceed mu into n, where n will be mg cos theta plus mv square by r sin theta. So if we take the mv square by r on one side, so we see that we get cos theta minus mu sin theta, and this should be equal to less than equal to, take mg on the other side, we get sin theta plus mu cos theta. So get v square should be less than equal to gr into this kind of term, sin theta plus mu cos theta upon cos theta minus mu sin theta. So see that v should be less than equal to square root of gr, and we can again use that trick, divide the numerator and denominator by cos theta. Get that this kind of relation. So from this we can see that maximum speed at which we can take the turning in this case will be square root of 10 into 50 into tan theta. Remember above was 0.2, and coefficient of friction is also 0.2.
Well, sir.
Okay, so this is clear. So now we move on to the next kind of situation in circular motion, in which we will incorporate vertical circular motion. Now, just keep in mind that the numerical problems of vertical circular motion in HC Verma are in the work by energy chapter. They're not in the circular motion chapter, because work by energy comes after circular motion, and there is application of work energy theorem or conservation of mechanical energy in these type of problems. So, okay. But you're already familiar with work by energy, so we will just do this as a continuation of circular motion. But as we solve these problems, we will understand how to incorporate conservation of mechanical energy as and when required. So imagine we have a situation like this. We have a hemispherical surface which is smooth. Okay. And on that surface, we release a particle by giving it a very gentle push at the top. There is a particle P sitting at the top of this smooth hemispherical surface. So a particle P of mass, let us say 500 grams, is initially at rest at the top of the surface, which has a radius equal to 20 meters. Now, the particle is given very gentle push. So its initial velocity is still tending to 0. Okay. And it starts sliding. Down the surface. So now what we want to do is, at an instant when its angular displacement from the initial position, when its angular displacement is theta, find the speed and normal reaction and as a function of theta. And we will also find out the value of theta at which it slips off. You'll understand intuitively that the particle will not come all the way down in circular path. Instead, it will slip off the surface, lose contact with the surface, and go into a projectile motion at some stage. We want to find the value of theta at which that happens. It slips off the surface. That is, it loses contact. So by definition, vertical circular motion is a circular motion which happens in the vertical plane. Remember, circular motion is motion in a plane. It's a two-dimensional motion. So if the plane of motion, the two-dimensional plane in which the circle lies, it happens to be a vertical circle, then it's simply called a vertical circular motion. Okay. So just take down the values in the question first, then we'll discuss what to incorporate. So the important thing here is that the surface is smooth. Okay. So that means as the particle is sliding down, there are only two forces acting on it, the weight and the normal contact force. Now, if you think from a work energy point of view, you understand that weight is a conservative force. Okay, so the work done by weight or the change in gravitational potential energy, whichever you take into account, it only depends on the vertical displacement. Okay. Whereas normal reaction is continuously acting radially outwards, whereas the instantaneous velocity is tangential. So what about work done by normal reaction? As the particle is sliding down the incline, is there anything particular about work done by the normal reaction force that we can incorporate?
So since it's always perpendicular, it should be 0.
Yes, very good. So normal reaction will do zero work. And gravity is a conservative force here. So that means if we take Earth plus particle as a system, we can conserve the mechanical energy, right?
Yes, sir.
Yes.
So as the particle starts from rest at the top, now as it slides down and reaches somewhere here, it gains kinetic energy, and that gain in kinetic energy will be equal to the loss in gravitational potential energy. So we can easily incorporate that to find the speed v. We will find one more thing as a function of theta. We'll also find the centripetal acceleration and tangential accelerations as functions of theta. Okay. Okay, so in any problem of vertical circular motion like this, where there is no non-conservative force like friction involved, you immediately understand that application of work energy becomes an important aspect of solving the problem. Okay. So after some time, if the particle has slid down from the initial position to somewhere here, let's say, okay. So it's made an angular displacement of theta. So between that initial point where it started to this point, it has a tangential speed v, and the forces acting on it at this point of time, if you think in terms of free body diagram, are weight and normal reaction. So let's say we're taking A to B. Normal reaction is perpendicular to the velocity vector at any instant. So that means n dot v is 0. So that means work done by normal reaction is 0. So therefore we can say that the change in kinetic energy plus change in gravitational potential energy is 0. So if the particle has a height difference from here to here is h. So from A to B, we can say that the change in kinetic energy is plus half mv square. The change in gravitational potential energy is a loss of mgh. So V is equal to root 2 gh. Now you can see that you can incorporate trigonometry here. So this is a circular arc. So when you drop this perpendicular here, this is r cos theta. This is h. So that's how we get the speed as a function of theta.
So we could have done this also by a work energy theorem.
Yeah, this is work energy theorem only, but we are applying conservation of energy because we are
Okay.
taking this is by applying work energy theorem to the system being the particle plus the earth. So for this system, you can see there is no external force doing work. There is no non-conservative force doing any work. Okay. So there is conservation of energy. Yes. Okay. So this becomes your speed as a function of theta. Now resolve the forces. Okay. Now come to the free body diagram. Okay. Resolve forces into radial and tangential. And from that find tangential acceleration, centripetal acceleration, normal reaction, all these things as functions of theta. Okay, so now looking at the free body diagram.
Okay.
So after resolving the forces, see that this is mg cos theta, sorry, mg sin theta. The normal contact force. And the particle has a centripetal acceleration and a tangential acceleration. Now the centripetal acceleration we already directly know because it's v square by r, and v we saw above is square root of this much. Sorry, 2. Okay. So substitute this here. So centripetal acceleration, you'll see, will become 2g into 1 minus cos theta. So in fact, now from this we have mg cos theta minus normal reaction is equal to mv square by r. So normal reaction So when you substitute this, you can see normal reaction will become mg into 3 cos theta minus 2. So this is normal reaction as a function of theta. And you can also see along that, so this is the centripetal. Okay. And along the tangential axis, we have only one force, the component of mg. So this gives us the tangential acceleration as a function of theta, so g sin theta. So now we've got centripetal acceleration as a function of theta, we've got tangential acceleration as a function of theta, we've got normal reaction as a function of theta. So that was the second part. And finally, from this, we can see the value of theta at which it loses contact. So for the particle to lose contact, that is slip off the surface, n should become 0. So from that you can see.
Done, sir.
Okay, so the final part, you have to find theta at which the normal reaction becomes 0 or it loses contact. Okay, so you can see that from above. So that happens at cos theta equal to 2 by 3 or 0.67, or theta is cos inverse of 0.67. We can leave the answer this way, but also using a scientific calculator or a table, you can see that this value will be approximately close to 50 degrees, I think. Let me just check. Yeah, 48 degrees, almost 48.2 degrees. So a little bit more than 45 degrees it will go to, and then lose contact with the surface. So as it loses contact, from there it will fall in a projectile motion instead of continuing in circular path. Okay. So from an angular displacement of 0 to 48 degrees or so, it will be in a circular path along the surface in contact with it. That means the normal contact force will be non-zero. But at this angle, it suddenly loses contact, and from there onwards, it goes into a parabolic path, projectile motion. And finally, it will hit the ground below. Okay, so there are various different situations of vertical circular motion like this. We have only discussed one example today. There's the standard situation of a particle attached with a thread, okay, the type of setup you have for a pendulum, but extended into a vertical circular motion instead of just to and fro. So we'll look at that also in the next lecture and more such applications. Okay. So a couple of more lectures and we'll complete the vertical circular motion and then move on to the next chapter, which will be center of mass after circular motion. Okay. So as I said that you can work out questions from the second part of work energy exercise in H.C. Verma, which will incorporate the vertical circular motion questions. So we'll discuss about that also. Okay. And of course, you can complete H.C. Verma's circular motion chapter, which will be up to the application of centrifugal force. So that's it for today's session, people. Wish you all the best. Have a nice day.
Thank you, sir.
Sir, will you share the file? Thank you, sir.